Okay. G sharp's up. then now that we have the sun, we have The Lost Kite by Kathy Niman. And we have a starry night now. now that we have a starry night, now we find Uranus is Spinning by Carolyn Miller.
Thank you so much, Kim. We really appreciate it again. That was really beautiful.
My string was going, I don't think it's going to break. It's just, I think it's unraveling because the heat in this room is just kind of stifling.
Strings will do that. Well, thank you again so very much. We really, really do appreciate it. And you bring a real special touch to our announcements, and it's a great way to start a meeting.
Well, thank you for having me.
And
everybody, thank you.
Well, thank you. And I guess it's now time to welcome everybody to the September meeting of Orange County Astronomers. We're getting ready for a new school season anyway. We still have 3 months until the end of 2021. One thing I would like to mention is, I guess, first of all, I should say, in case you don't know who I am, my name is Barbara Toy. I'm the current president of this organization, which is a wonderful position to hold. And it's my great pleasure to welcome you all. And I should also mention that we will have elections coming up in the not too distant future. Next weekend, next meeting, we will start taking nominations. So if you would like to have a hand in administering this wonderful club, and I say that without any bit of sarcasm, believe me, I love being on the board. That's why I'm where I am. I think most of the board members do enjoy that, but we mustn't be selfish. So if any of the rest of you would like to try out, send your request, let Alan Smallbone know that you are interested in being on the ballot. And as I said, we'll start that formally next month. We will close up nominations in November, and everybody will be voting in December. And we'll welcome the new board in January, just so you know the schedule. So that's the schedule for our wonderful election cycle. And now we will get back to the schedule for our meeting. And it is my pleasure to turn this over to Kyle Graham, who will take us through the club announcements. Thank you, Kyle.
All right, here we go. Right, so actually tonight we're going to start with Cecilia and her crew for the first few slides.
Yes. Well, welcome new members. We hope you enjoy this meeting, and we are so excited to do astronomy with you. Okay, so ANSA is on hold for a bit. We're discouraged from going. As you can see from this, some things are going on online, like the board meeting coming up in the beginners class October 1st, also online. Okay, so outreach. School has started, as Barbara said. Fall is here, living school and everything. Some students are still online, but the ones that aren't, some schools are actually asking for October, November bookings. And if you guys are watching this and you don't have a telescope, but want to volunteer anyway, Alan, if I found the announcements, would generally loan you out something to share with the wonderful scholars that are out there looking for knowledge from us. So if you would want to volunteer, please go ahead and reach out to outreach at astronomers.org to be added to our new and improved and awesome, wonderful list of volunteers. Thank you all.
Hello, my name is Dalila. Thank you for being here. And today is going to be a waxing puzzle. Make sure you look out and see the moon.
All right. For the Sirius astronomer, we're always looking for new articles. They can be put in images, observations, etc. So if you have anything that you would find interesting and would like to put in the Sirius astronomer, please send the article to Dave Fisher for review and consideration. If you would like to not get your Sirius astronomer mailed to you every month, but would like to just read it online as it's available on the club website in an electronic format, please, there should be instructions on the website, and please send an email to Charlie. members are still being discouraged from going to the ANSA site as the club does not have the capacity to be able to sterilize the site or enforce COVID-19 guidelines. But if you do have a pad out there or any other things out there, weed clearing still needs to happen as fire danger doesn't go away because of COVID. So if you do are able to help or do have a pad, please do weed clearing at your convenience. So John Garrett will be up next with the What's Up presentation.
I was able to attend a star party for the first time in about a year and a half, just last weekend, at the Joshua Tree National Park Night Sky Festival, and that's where this first photograph comes from. I had planned to take wide field photos as I also shared my telescope with people, but due to a multitasking error, it turned out that all my wide field photos were terribly blurred. But fortunately, someone had my back. A high school student, Marin Cantrell, ended up using my telescope mount to do some photos, but also did a lot of photos on her own. And so I'm going to be featuring a few of her photos tonight. So this is her photo from the early part of the National Joshua Tree National Park Night Sky Festival just last weekend. And I'm using a second photo of, just a moment. I'm using a second photo of hers to illustrate the point that this September strikes me as a very busy month, astronomically speaking. So I'm using her photo of star trails plus airplane trails to give you that look that there's really a lot going on. We have some of the brightest planets are still visible in September. We still have the Milky Way visible. And if the Milky Way is visible, there is just so many objects no one could cover in a night visible. So September really is like one of those nice last chance opportunities to see what I think is a very pleasantly busy sky. And here's first I'll talk about the moon schedule. And this is also one of her photos that she sent me, that she took of the moon. And first quarter moon is early next week. Full moon comes the 20th this month, and third quarter on the 28th, and then new moon on the 6th of October. But I always look at these events in terms of what it does for weekend getaways. So if you want to get away for some good dark sky right away, this weekend is about your last chance at it. And if you can get out away from the cities this weekend, you'll have great viewing from midnight onward. The moon dominates our calendar really for the next 2 weekends, but on the 2nd of October, that will be dark most of the night. So that's a good weekend to get away. And likewise, the following weekend will be a mostly dark sky weekend. So good times to plan your getaways. If you went outside tonight, or actually last night, and looked west, you might see this view. This is a photo from my front yard showing where Venus is just setting behind the mountains in that picture. And then the moon is just a little bit above it to the right. And the Venus is going to work its way this way over the next month. So it's going to be setting a little bit later. It's also getting closer to us. So if you view it through a telescope, you'll start to see some change in size of the planet over the month. And it's getting closer to the half Venus phase stage, not quite a crescent Venus yet, but it's going to be like a gibbous Venus throughout the month. And then the moon, of course, is now out of the picture and circling around us, but it will take the moon almost a full month to catch up with Venus again to get a conjunction of Venus and the moon. Now, if you look a little bit to the left from where this picture was taken to the east into the south, that is the southwest, you'll see Scorpius and Sagittarius. And these two constellations are getting low. It's a sign that these two are starting to leave us soon this time of year. And then if you swung your camera another field to the left again, and you're looking in the southeast, you'll still see the bright planets, Jupiter and Saturn. So they're low in the sky, so that creates a lot of atmospheric disturbance for viewing them, but they still are quite pleasant to view. I was viewing them at the Joshua Tree Night Sky Festival, and they look pretty good even in turbulent air. So definitely try to get a view of them. They will stay up for a while throughout the night. I took this photo later on that same weekend at 2 in the morning, and this is Jupiter and Saturn down below it, and it's tilted because my camera was on a mount, a polar line mount, and it wasn't convenient for me to orient it correctly with the horizon. But they'll stay up there for a while. So I wanted to confirm that if you stay up till 2 o'clock, you'll still have a view of Saturn and Jupiter. And here's the constellation Capricornus, and Saturn and Jupiter are about here where I've drawn them. And Neptune is about approximately up here. So if you're looking at Jupiter and Saturn, it's also a good time to catch Neptune. And Neptune is at opposition, means that Neptune is going to be as big as it's going to get for the year, but you will need a high power telescope to make out any size of Neptune, but it's certainly worth looking at while you're in the area. And this constellation here is Aquarius, and it also has some very nice deep sky objects. So you're already out there, you're looking at Saturn, you're looking at Jupiter, maybe you're looking for Neptune, but you should also look at various of these deep sky objects that are in the area. One isn't that exciting, it's M73, which I think is just a group of stars that was thrown into the Messier catalog, but that's just so you know it's there. But right near it is M72, which is a nice little globular cluster. This one's viewed in my 8-inch Smith Cassegrain telescope, so you do need some good magnification to see it, and at least an 8-inch telescope. It is going to appear fairly faint. And then this one, M30, is photographed here in my 3-inch telescope, my TeleVue 76, and it shows up pretty brightly. So this one also shows up pretty nice in the telescope. And then, of course, if you're looking near at Saturn, you might as well swing your scope over to the Saturn Nebula. If you have a big scope, you may be able to see the projections that give the Saturn Nebula, NGC 7009, its name. And this was taken again in my Cassegrain 8-inch at f10 and cropped, so it's a little bigger than it appeared in the photo. And this one, Helix Nebula, I don't believe is a visual object, but it comes up pretty well with a small telescope. So here it is in my 3-inch telescope where I started to stack images. I stacked 5 of them because that's all the patience I have for taking pictures. And so 5 of the same kind brought out the Helix Nebula pretty well. And then M2, here's M2 in a 3-inch scope. And in an 8-inch scope, M2, I think, is almost as good as some other famous globular clusters in the summer sky, such as M13 and M22. But I think M2 gets overlooked a lot. It's pretty far in the south, and it's often overshadowed by the M22 and the M13 that's also out in the summer sky. Anyway, back here to our photographer, Marin Cantrell, and her picture. This time of year, this photograph is a good reminder that the Milky Way passes directly overhead in the early hours of the evening. So you've got the whole Milky Way before 10 o'clock that you can scan any part of it. And there's just no way of me to cover everything that's in it. And if you start out fairly low, you might see actually from there, go up from that last picture, you pass Aquila, the eagle, and then get into Cygnus, the swan here. And this particular photo I took at 2 o'clock in the morning the previous weekend. So the Milky Way has rotated over into the west. And as I usually draw Cygnus, Cygnus is now upside down. And one of the things I noticed in my picture, and I'm not using a very good camera, I'm using a pancake lens, they call them, a 24 millimeter, and not a very impressive lens, but I was able to see a little green splotch in this picture. And if I take the actual image cut out and not shrunk down to fit on the screen, that little section is M27, the Dumbbell Nebula. And so I think you'd be surprised that you might be able to catch a number of these things in a lens. And I know a lot of you have better lenses than my 24 millimeter pancake lens in which I caught this one. If you go even farther from Cygnus to Swan, you'll see Cassiopeia. Cassiopeia rising in the northeast is full of rich objects. You can see right here the double cluster. You can see that with the naked eye at a dark site, as well as in binoculars. And a little farther from there is a constellation that is now becoming one of my favorites for all of the items in it, Perseus. And you can see, here's a little sketch of my Perseus character, but in Perseus, you've got the Pleiades nearby, always a pleasant sight. You've got the California Nebula here. You've got open clusters here. You've got other little clusters. Oh, yeah, here was the double cluster. A beautiful sight as it continues the Milky Way as it descends off into the northeast. And this is also a reminder of fall is upon us. And I always think of Perseus as one of the classic fall constellations. So a little bit in the morning sky. If you're up till 2 in the morning, as I was, you might as well wake up at 5 because you're not going to get much sleep anyway. And here's looking east a little bit before 5 o'clock in the morning from where we were last weekend. And this is the bright star Sirius and the cluster, open cluster M41, all in Canis Major. And just a little bit above that is Orion. And if you can catch Orion in the blue hour of the morning, you may be able to see a very strong contrast in Betelgeuse, the red star that gave us a scare last year in dimming excessively to the point where people were discussing whether it was due to explode again and due to explode supernova, that is. It didn't. It's going to be there for probably a good long time, but it's always fun to wonder about. And that's just a little snippet of what's in the sky, a very busy time of the year from the Milky Way, the bright planets. So I hope you get out there and enjoy. Thank you.
Thank you very much, John. That was a great presentation, and we get a lot of information we're going to go observing soon. Hi, my name is Reza. I'm the Vice President of the club. I too would like to welcome you to the September 10th, 2021 General Meeting of the Orange County Astronomers. Before introducing our speaker of the night, let me remind you that if you have any comments, you can use the chat section to send it to us. And for asking questions from the speakers, you can always use the Q&A section during and after their talk. Our speaker at this meeting is an associate professor at the University of the Western Cape, South Africa, who's joining us around 5 a.m. their time. Trained in physics at EPFL in Switzerland, she holds a PhD in cosmology from Cambridge University, UK. Her work has earned her numerous awards, including an International Astronomical Union Special Award for Astronomy Outreach, Development, and Education, and Mail & Guardian Top 200 Young South Africans. Please join me by clapping your hands virtually in welcoming Dr. Carolina Ottman. Dr. Ottman.
Hi, good evening and good morning from this side of the planet. I think we are pretty much at opposite sides. I think Hawaii is really the opposite from here, but but we have similar climates. So yeah, and I was very excited to see all the really beautiful things that you can see in the night sky on your side. So I hope we can take out the telescopes around here as well and go and take a glimpse of the joint objects that we can see. Obviously, Sirius and Orion is a half a year constellation for us, and to us it's upside down, if you will, if you imagine it as the hunter. So it's really fantastic to see. So I'm going to share my screen. There we go, and I'm going to put it on. So I have two monitors. There. You should be able to see the title slide. Oh, it's gone already. There. Can you see it all right? Okay, perfect.
Yes, all good.
Okay, so firstly, thank you very, very much for this invitation. I'm always thrilled at any opportunity to be able to tell you a little bit of the story of astronomy in South Africa, because South Africa is it's a country in Africa with all the privileges of an African country, an amazing night sky, but also all the challenges, the social challenges. And as you will have heard in the introduction, I I am quite vested in development, outreach and education as well. So I'm going to tell you the scientific story of astronomy in South Africa, but also I'm going to touch upon some more on the ground issues and see how they weave together, because they really do quite profoundly. So as Reza said, I work at the University of the Western Cape, and I'm at the Inter-University Institute for Data Intensive Astronomy. So I'll tell you along the talk what this institute is about. But first, I want to show you what how modern astronomy started in South Africa. This clip here shows you about a century of colonial shipping between 1750 and 1850, and shows how the global ships would have crisscrossed the planet, and in term, for trade of various kinds. And you'll see a lot of them touch this southern or southwestern corner of the continent of Africa, which is where Cape Town is and where I am. And modern astronomy in South Africa really started because there was a need to map the southern skies for navigation purposes. And so for this to be possible, let me see, I'll just stop this now. There we go. There was the observatory, the first observatory, astronomical observatory, was set up in Cape Town. It was known as the Royal Observatory in 1820. And attached to the observatory were cannons. And the role of these cannons was not to shoot down any ships coming into the harbor of Cape Town or anything, but rather to shoot every day at noon so that the clocks on the ships could be set. Because obviously time is essential. Knowing what time it is essential when you're navigating by the stars. So with a map of the southern stars and a time calibration set up at the harbor of Cape Town, ships were able to then navigate in the southern hemisphere. And in fact, this gun, which we call the noonday gun, is still very much a tourist attraction. And it even has its own Twitter feed where every day at noon South African time, it just tweets bang. In fact, because it still fires, not bullets, but it just makes a loud noise. So every day at noon in Cape Town, you hear a loud bang, and then you know that it's exactly 12 o'clock. So the origins of modern astronomy in South Africa is very much entangled with colonial times and with colonialism. And there's a reason I mentioned this, because I'm going to come back to this in a little bit later. So the Royal Observatory in Cape Town was set up in 1820. There was another observatory in Johannesburg, and they emerged in 1972 when the Royal Observatory in Cape Town was returned to South Africa, or rather was gifted to South Africa by the UK. So Britain was still in charge of the observatory until 1972, and only then did it become a South African institution. And it became the South African Astronomical Observatory, SAAO. So last year, SAAO celebrated 200 years of existence in South Africa. And among some famous astronomers, we had Herschel, for example, who was a very keen astronomer, but also very keen on the flora, the unique flora that we have in this part of the world. And then in terms of radio astronomy, and I'm going to speak mostly about radio astronomy tonight. NASA actually installed a satellite monitoring dish in South Africa. This is much closer to Johannesburg than to Cape Town. And they installed it in 1960, operated it until 1975, where the South African government got to take it over. And then it became what we call HARTRAO, so Hartebeespoort Radio Astronomy Observatory. Then in 2003, South Africa embarked on a SKA project. So SKA Africa was the name of the project at the time. And in 2018, HARTRAO and SKA Africa joined to form the South African Radio Astronomy Observatory, which we call SARAO. So we have SAAO and we have SARAO for optical infrared and then for radio. And so this picture is the satellite dish that NASA installed in 1960. It's still operating. It's an enormous dish. I've been on top. I've been standing on the edge. It's an incredible piece of technology, and it works still beautifully, which is really quite amazing. So I've mentioned the Square Kilometer Array. The Square Kilometer Array was dreamt up by astronomers in the 1990s. And what they really wanted to do, they dreamt of a radio telescope so big that the technology to build it and to process the data from it didn't yet exist in the 90s. They basically wanted to turn planet Earth into a giant radio eye to peer deep, deep, deep into the universe where nobody has been able to peer before. And in 2003, as this SKA organization existed and started opening up a sort of a competition and a bidding competition to host the telescope for a location for the telescope, South Africa decided to enter the race to host the radio telescope in partnership with 8 other African countries. So Botswana, Ghana, Kenya, Madagascar, Mozambique, Namibia, and Zambia, and Mauritius as well, sorry. And so this was a very competitive process. After a while, there was only 2 countries competing. And in fact, in 2012, when it was awarded both to South Africa and to Australia. South Africa is going to have 2 of the wave bands, and Australia is getting 1. So this is, we are very excited. The full SKA is going to be composed of 3,000 dishes that span starting from a spiral in South Africa all the way out to Ghana. So it's a really, really exciting project, and it was a purely competitive project. And I know a lot of astronomers before it was awarded to South Africa who wouldn't give South Africa a chance. They said, no, but South Africa, you need political stability and this and you need that. But, South Africa came out on top and put in a really, really good bid. And this has had a really big impact on the country. So I'm going to touch upon that in a minute. In 2018, the Meerkat radio telescope was inaugurated. So the Meerkat is a precursor telescope to the SKA. So because the technology when the SKA was imagined didn't exist, there was a whole stage of pathfinding technologies and pathfinder telescopes followed then by precursor telescopes, which now will turn into the SKA, because construction has been actually green-lighted by the SK Observatory, which is the international intergovernmental organization, that the SK organization has become in 2021. So this is all ongoing, but in the meantime, the Meerkat telescope is actually producing science. But first, let's look at the science goals of the SK as a whole. There we go. I think, there we go, right. So the science goals of the Square Kilometer Array is to understand galaxy formation and evolution over cosmic time. It's also to test gravity in conditions where the fields of gravity are very strong. So for example, around the supermassive black holes in the center of galaxies. Also to probe the origins and the evolution of cosmic magnetism. Where do magnetic fields in the universe come from? Probing the cosmic dawn. This is really trying to peer into the time where the very first stars lit up after the Big Bang. So this is just a few 100 million years after the Big Bang, when the first stars would have lit up space around them. Try to look at that very, very first generation of stars. And then also the cradle of life, the origins of life in the universe, but also the search for extraterrestrial intelligence. And in fact, you may have heard of the Breakthrough program because I think they're based in California, and the Breakthrough Listen project is a collaboration with the Meerkat telescope to put some hardware on our dishes, to actually measure and look for signs of extraterrestrial intelligent life out in the universe, which is really, really exciting because it's getting increasingly a serious consideration by astronomers. And I think the most exciting of science cases is serendipity. The SKA is designed to find what we have no idea is out there. The whole idea is to just be able to discover to discover the unsuspected and the unimagined yet. And this is such a beautiful science case for an instrument like this. And it is really quite inspiring that in this day and age, we're able to build such a large scientific infrastructure with just plain discovery as a science case and not justify everything with a very utilitarian purpose. So it's a very, very inspiring instrument, if you ask me. But it's also a very big data machine. So in this plot, you see just a sort of data flows that we're expecting from the SKA, and only a small part of it. This is the phase 1, so not the full construction. It's just a few hundred dishes, and it's only the South African mid array. So this is only one of the 3 bandwidths, and it's only the South African component. So already you can see, you know, if we're looking at, 300 petabytes per year in terms of data, it is enormous. It really, really is. And so, you know, we really need to also develop the computer science and the computer infrastructure to be able to manage such intense data flows. So this is a picture of the Meerkat. This is now the South African precursor telescope to the square kilometer array. It is a beautiful instrument. I've been there on site and it's just mind-blowing. So it's 64 dishes that are, okay, so you will excuse me, I am comfortable in the metric system and I don't really know, I wouldn't want to try to translate that on the fly into feet and miles. But so the dishes are 13.5 meters across. So I guess that's probably about, I don't know, maybe 14 yards or something like that. And the interferometer baseline, so the distance between 2 single dishes, varies from 29 meters to about 8 kilometers. And so this makes, so this is the 64 dish Meerkat telescope. And it's just an incredible instrument. In terms of data rates, it maxes out at over 1 terabyte an hour already. So it's already a very, very large machine. So what's the science that we'll do with the Meerkat specifically? So this image here is the image that was published at the inauguration of the Meerkat. It's a radio image of the center of the Milky Way. And it's an absolutely incredible image. It's the biggest, the most detailed view of the center of the galaxy in radio ever. And as I was telling Reza when we were planning this, when I was an undergraduate, the first images came out of a Hubble Space Telescope. And it was just so incredible, and it definitely played a part in me ending up studying astronomy. But I think, you know, these radio images that we're getting now, and I'm going to show you quite a few, really bring radio astronomy into the realm of these beautiful, incredible images that we can get of outer space, something that we would just not ever have been able to see were it not for this beautiful infrastructure. And so the Meerkat science is divided into sort of 2 types of projects: the sort of single observation projects, which are open time projects, and the director's discretionary time take up about 1/3 of the telescope time, and 2/3 of it is 8 large survey projects, right? So from pulsar timing to deep neutral hydrogen studies, to explosive events, transient events, but also continuum surveys, which means, you know, looking at a whole field to see what is in there, and absorption line surveys. But one thing that the Meerkat is very, very good at is looking at the 21 centimeter emission of neutral hydrogen, so H1, as we call it in here. And this is a fairly rare orbit jump of the electron in the single hydrogen atom. So it's a very faint signal. But if we look very, very deep in the universe, you know, neutral hydrogen there was a lot of it. And finding that neutral hydrogen enables us to trace the formation and the evolution of galaxies like no other probe. And so it's really, if it's a faint signal, the Meerkat is really, really good at capturing it. So the projects here, that are in italic, Mongoose, Fornax, Laduma, Thundercat, and MIT, are those that are supported by IDEA, the Inter-University Institute for Data Intensive Astronomy. So what is this institute? So the institute is actually a partnership of 3 South African universities with the South African Radio Astronomy Observatory. So the University of Cape Town, the University of the Western Cape, where I'm based. So both those universities are in Cape Town, and the University of Pretoria, which is the capital city next to Johannesburg. And IDEA was really set up to enable the South African research community to be able to make use of the data coming out of the Meerkat Telescope. And the reason for this is that, well, such a facility didn't exist before. There wasn't such an institute before. And were it not for that, the data would be shipped to, to richer countries where beautiful data coming from Africa would be processed and analyzed, and discoveries would be made by other scientists. So we really wanted, the point of having the SK in South Africa is also to benefit South Africa. So one of the things to make that possible is that we built a cloud computing facility specifically for research. So what you see in this slide are the specs of this cloud as it currently is. So it's a fairly modest facility, especially comparing to, the large data centers owned by the large the tech companies like your Googles and your Facebooks and Amazon and so on. But it's all built on open source technology, and it also is designed specifically for the processing of very large data sets. In astrophysics, of course, but it turns out that we're also supporting bioinformatics and genetics data, which is also a very important topic for Africa, because Africa has the largest human genetic diversity of any continental human group. And it only makes sense that this data should also be researched by African scientists. So we said the Meerkat is a fairly big data machine at 1.1 terabytes an hour. So this is how this data actually travels down to our facility, to our cloud computing facility. First, the signal is captured by the telescope, and there it's digitized and amplified. Then the raw data goes from all 64 dishes, you can see on the right here, all the way to a central Karoo array processing building. The Karoo Desert is where those dishes are built in South Africa. And so the signal from the 64 dishes are coming to this giant supercomputer that correlates those signals. But so this is a supercomputer. It's got 10 petabytes on-site data storage. And but you can imagine that a giant supercomputer will create a lot of radio noise. So how can we have such a big supercomputer on site where the dishes are? Well, simply it's completely and fully underground. It's really quite, I wouldn't be surprised if a future James Bond movie were filmed there, because it's really the full computer, massive data centers actually underground near these dishes. So when the data comes and is correlated, then it has to travel down to Cape Town. And on the left panel here, you see the coastline of South Africa in this fine blue line. And the thicker lines it's the optic fiber network that we have. So there's 2 paths. There's a backup path as well that of fiber that form part of the South African National Research Network that we call SANREN. And that comes down to Cape Town, to the Center for High Performance Computing. And then on the right-hand side, you see that IDEA, our cloud computing facility is about 1 kilometer away from there. And so that's how we get this data into our cloud. And I'm putting it here because it really is not a trivial exercise to make such a large data rate come down and be able to be processed by the scientists. But the Meerkat is not the only source of data that IDEA receives. This is the Meerlicht telescope. Meerlicht is unimaginatively named, it just means more light. This is an optical telescope. It's not very large. I think it's a 1 meter telescope. That's in the other site where we have optical telescopes and infrared telescopes in Sutherland. We also have a Cumbria set of telescopes there. We have the Southern African Large Telescope, which is a 10-meter class optical telescope. So we have a number of telescopes sitting there in Sutherland. And the Meerkat is designed to look exactly at where the Meerkat is looking at exactly the same time. Obviously at night only, because it's an optical telescope. But this allows to have simultaneous optical and radio observations, which is really important for example, transient detection, to gain immediate optical counterparts to, for example, spot the source of a transient event. So the data from the Meerkat telescope comes straight to IDEA, our institute, for processing. Another thing that we do is that when we have these large data sets, we need to be able to explore them. And so we do quite a lot of development and research in data visualization. We've developed software to explore these vast data sets in using immersive technologies, digital planetarium. So we have a digital planetarium in Cape Town that is part-time for the public and part-time for scientific research. So you can literally go and explore the large data set in a dome environment. We have also other immersive screens. We have a panel of 4K screens that enable both large views and detailed views. And we also have developed virtual reality software to be able to explore the data, because the data we're looking at is essentially either volumetric data, or so large data cubes, or it's point sources, both of which can be rendered. And because of that, we are able to apply the software to other uses as well. So this, in the circle at the bottom here, you see a mouse brain being explored using virtual reality. And I think it's some functional imaging that some biologists did there. So really, and what's really interesting with these visualization software tools is that the data cannot be downloaded to the computer, for example, the laptop on which the VR runs. It has to be streamed because the data is just so large. So it has to come as the user asks for it, and it has to be rendered on the fly. And so another piece of software that we're very much involved with is the cube analysis and rendering tool for astronomy, CARTA, which so you see in action on this slide. And this is really also, it's a server client-based software tools where the large data sets, you can have a terabyte, a couple of terabytes of data sitting on the server, and this will enable you to interact with it and to explore your data set streaming-wise with the rendering on in the client side of the software. So you can imagine that a software like this really accelerates the journey from data, raw data, to the science. And in fact, if we look at our institute only, IDEA, since 2016, when it started really operating, over 100 publications have come out already of our institute, whether it's in astronomy or computer science, but also in scientific infrastructure and data visualization and so on and so on. So I'm going to show you a few of the discoveries that have been made with the Meerkat Telescope. And this is, I think, where you'll see that we've really entered a new age of imaging in radio astronomy. So this here, so I showed you, let me just go back a few slides. I just want to point out this image, as I said, the center of the galaxy here. This is the heart of the Milky Way. And this image is absolutely unprecedented. And I will come back to it later again. It's such a beautiful image. But this image is the same here. Let's go, there we go. But I've turned it so that the Milky Way in the slide appears vertically. And you can see that there are these incredible structures. So the reason I've put it vertically is that you don't focus just on the Milky Way, but you kind of see these bubble structures, these massive bubble structures extending way beyond the plane of the galaxy itself. And so these giant bubbles is the first large publication that came out with the Meerkat observation and uses that first detection of and first imaging of the galactic center. And it really is these, so you know, on the left and on the right, you see it's like this bubble that has been ejected from the giant, the supermassive black hole at the center of our galaxy. And so these structures are, are being studied. They've never been seen before. And so this first paper came out in Nature in 2019. This image is not done being studied. This one paper has come out of it, but there are many more to follow. And we'll look a little bit at the structures in a minute. This one is a picture of thousands of radio galaxies. Every single dot here is a radio galaxy. So it's in the front there, the Meerkat radio telescope is overlaid. This is actually to scale. So it shows you what the Meerkat is able to observe in terms of coverage and in terms of survey capabilities. And so you can see quite a few radio galaxies where you see the typical 2 radio lobes at the bottom right and upper left quadrant. But every single dot here is a radio galaxy. There are some that I think there's a few stars, but basically this gives you, if you have radio images of thousands of galaxies like this, and they're all at different stages of their evolution, and some of them are very, very ancient, very far away, and some of them are more nearby. And so if you have a story like that of thousands of galaxies throughout the whole cosmic history, you're able to piece together bit by bit the history of galactic evolution, the evolution of galaxies, how they've evolved from the earliest times in the universe to today. And so something like this is an incredible data set. And so, for example, in this result, they found that the far infrared luminosity of galaxies is a slightly sublinear, so it's slightly less than a linear relationship to the 1.4 gigahertz luminosity, which is what is measured in this image. So 1.4 gigahertz being one of the frequencies that the Meerkat telescope can observe. So this is just absolutely incredible to see. Imagine looking up at the sky and everything, you see all these galaxies. It's just incredible. This is another beautiful discovery or a mystery solved by the Meerkat telescope. So there's this incredibly beautiful radio galaxy. The galaxy itself is like a disk, and you can see it in the lower image as this orange ellipse there. But this galaxy has very strange lobes. They sort of form an X. And so it's an X-shaped galaxy. So what is happening there? So in 1984, it was conjectured that this was backflow of gas from the jets towards the galaxy that was then be deflected by the galaxy. And in fact, now this has finally been confirmed using radio astronomy imaging, but also polarization and things. So with imaging and measurement of the gas and also of its polarization, and the astronomers have been able to develop a velocity field. And what you see is that it's generally indeed backflow that's coming from the large lobe and so being deflected by the central galaxy and going out in another direction. But also where there's a lot of turbulence, the polarization goes down, means that there's a lot of interaction because the polarization sort of gets then changed into polarization in all directions. So residual polarization is very low in the very bright region there. And so if you look at the small inset image at the bottom there, you can really see the youngest jets coming out of the central black hole. And these are more older jets that have come out and are flowing back and are sort of bouncing off. And this is just incredible to be able to see. I don't know if you've ever seen anything like this before. Now, the next one is just, I think it's one of my favorites. Just look at this image. I mean, this is a radio image of a radio galaxy. You can see the galaxy is right at the center there. You can see on the top image this little central part there from which these massive jets come out. And I mean, the image like this looks more like some deep sea jellyfish than, bioluminescent jellyfish rather than a galaxy out in space. But that's exactly what it is. And so it's not only beautiful, but it has a lot of features that have never been seen before. So we know about the jets, and obviously here they're pictured in incredible detail. But what is completely new here is that we can see these threads that go from one jet to another. And so this is a huge discovery. How does that happen? And so from the observations, we can tell that it's collimated synchrotron radiation, but it's of unknown origin. We don't actually know what it is, this jet, these threads linking the two jets, so there's something more. These radio lobes that come out of a central galaxy that extend far beyond the stretch of the galaxy that would be visible in optical, for example, are actually connected and are interacting. So this is a whole new realm of structure that we need to understand and we need to explore. And so these threads, there's not just this one. This is a very famous, a classic Fanaroff-Rayleigh type 1 radio galaxy. And I mentioned the type Fanaroff-Rayleigh here, not to go into the details of what it means, but to mention that it's named after Bernie Fanaroff, who is a South African radio astronomer, but he's also a very famous activist. He was a trade unionist and one of the stalwarts of the fight against apartheid. And he was the first director of the SKA Africa project until just a few years ago. And so we really are honored to have somebody like this, who's both an astronomer who has had objects named after him and an activist, a political activist for the freedom of this country, been able to lead the SKA project in Africa. So this image of this very well-known IC4296 radio galaxy is also imaged in unprecedented details. And you can really see that when the jets hit the intergalactic medium, they get diffuse, and it's like, it's hitting the medium and it sort of dissolves like that. But you can also see just near the optical counterpart, the galaxy in the middle here, you can see below this sort of, again, these sort of filaments and threads that we need to figure out how they come. They also seem to connect the two jets. And if you look also, you can kind of see the sort of spiraling of the gas out from the central jet, which again has been sort of conjectured, but is now sort of directly imaged. And in this image, because it's overlaid with an optical image, you can see the sort of the scale of galaxies compared to those jets. And it really illustrates beautifully how much larger the jets are to the central galaxies. So this is some of the science, some of the recent discoveries that have been made with this telescope. There's many more. There's a mega maser that has been discovered just serendipitously while looking at neutral hydrogen. There's a lot of things coming. So you should really try to keep your eye on the South African astronomy news. I just want to come back to this incredible image of the center of the galaxy. I just want you to look at it and see all these incredible threads and structures and bubbles and things. So some of them are known, some of them are supernova remnants, but a lot of them are completely unknown. We don't really know what they are. And so I'm just going to zoom in on the right-hand side of the picture here. And I'm just showing this and leaving this here because I want you to imagine being an astronomer and seeing this and trying to figure out, but what on earth is all of this? At the top, you have this sort of wispy thing that almost looks like a number 4. Like, what is that? At a little bit lower, when you have this very big thread, there's like a bubble sitting there. There's also like something that looks like a front. Is it like, cloud formations where we have these sort of beautiful pressure waves going through that we can see? We don't know. We really literally don't know what this is made of. So the amount of science that is going to come out of observations like this is just unimaginable. So yeah, so this is just, this is what we can do with this beautiful radio telescope that's based here in South Africa. So the telescope is on the ground, but what else is happening on the ground in South Africa? Well, we have a very complex society. And in 2015, there was a number of students that started a movement. It started at the University of Cape Town, where the students decided to pull down the statue of Sir Cecil Rhodes, who was a colonialist, who both endowed the University of Cape Town with a lot of wealth, but also was one of the architects of the racially segregated society that South Africa ended up having to live with until just about 25 years ago. And so Black students who are mostly coming from very humble backgrounds reacted when there was an announcement of the increase of university fees. And they decided, no, this is not right. It makes university only affordable to privileged people. So this is not an equal society. This is preserving inequalities. This is really bad. So first they took down the Statue of Cecil Rhodes, and then they had this fees must fall protests. And they questioned the whole university system. And science itself was not spared by this. And a lot of academics were not very happy by this because, very scientifically minded academics who don't necessarily have an interest in social justice were thinking that, what do you mean? Science is not colonial. Science is just facts. But there is much more to it. And I'll come to that in a second. So obviously this made news and made news worldwide. There was a few cartoons in the newspaper. So I just have two here that I want to show you. I think this one is a very interesting one because it shows young Black people putting down a pale flag of South Africa, and that flag that has such bright colors that was really the symbol of a new South Africa has sort of paled and been overlaid by the fact that the society is still very much unequal and still very racist. And this cartoon, which if you're a South African, is very, very funny. So in South Africa, what you will often see when you drive on the roads is you'll see a white guy who will own one of those, we call them bakkies, pickup trucks, as a garden service or something like that, with a few unqualified, sort of low educated Black workers in the back. And, that's sort of how it works. And then the adaptability of the system to a revolution of students pulling down the statue of Cecil Rhodes is just, Bob setting up a statue relocation service and just putting it on the back of his bakkie, of his pickup truck with these workers. So the situation really hasn't changed. So, I mean, it's very ironic. It's a funny and ironical image. And I think one of the great things in South Africa is that we really are able to laugh at ourselves. So I hope you get the depth of this cartoon. I think it's very cool. But anyway, so really, demonstrations and protests like this are concerned with the social justice aspect of this. And so people ask the question, what is the point of investing in something like the SKA when we have so many challenges and we have an incredibly high unemployment rate? We have a lot of people who live in, below the poverty line. And so in fact, the South African government, when they decided to embark on the Square Kilometer Array, never did it just for the science itself. There was always a view that investing in the Square Kilometer Array would contribute to the development of society, whether it's the development of young people, the attraction of foreign direct investment, boost to the economy, especially the knowledge-based economy. Excuse me. And so right from the beginning, they started a bursary program and a scholarship program that was very generous, more generous than the normal state scholarships, and covered all the fields needed for the SKA, from mechanical engineering to electrical technicians to mathematics, obviously astronomy, computer science, engineering. And on the left, you have a list of areas of undergraduate bursaries topics. So this is now not the technicians, but this is at university specifically. And on the right, postgraduate scholarships. And so to date, well over 1,000 bursaries have been awarded. That means over 1,000 young people who have been able to study for the build up to the SKA that are either able to do systems engineering or able to do galaxy evolution or able to do, big data, computer science visualizations or whatever. And that really has a serious impact. And to just illustrate the impact of a program like this on a modest country like ourselves, I just want to show you the impact on my own university, the University of the Western Cape. The University of the Western Cape was set up in 1960. So last year, we just celebrated 60 years of existence. And it was set up originally for the colored community. So in South Africa, the society is divided in different sort of ethnic groups. And the colored society is not black, but it's not white. It's sort of in between. So it has, but it's not just mixed race people. It's also people who are indigenous to this area of South Africa, the Cape, that have Khoisan. There are descendants of the Khoisan, for example. And they have a sort of a fairer skin tone, and they have freckles. They often have green eyes, but they have, typical African hair. It's one of the very diverse groups of people that we have in South Africa, but they were classified as different from Black Africans from other areas of the country. And the university was really meant as a college to create, just some teachers and some nurses for that group of people. But it was very active in the fight against the apartheid regime. And in fact, the current democratic constitution of South Africa was in part written at UWC. So UWC has a beautiful, dignified history in law and social justice, but it also have a history in physics, but not in astrophysics. Astrophysics only started in 2008. And thanks to the bursary program, as well as to the South African Research Chair Program and the SKA Research Chair Program specifically, since 2011, we've graduated 16 PhDs, 28 masters, and 47 postdocs have gone through the UWC Astro Group. Currently, we have 6 staff, of whom 3 are A-rated researchers, so that means leading internationally. It's a ranking that the National Research Foundation has in South Africa, and I'm not one of them. So we have some really great staff, and we have 14 postdocs, and we have currently 24 postgraduates. And in 2016, Nature ranked UWC as the best physics department in Africa. So really, and this is, UWC is a publicly funded, historically disadvantaged institution with fewer resources, and it's competing on the continent against private universities and everything. So it's really the impact a program like this has, on small universities like mine is really quite large. And so how have we managed to get so many students through? Well, we have several messages. One of them is that, and it's a conviction of the government as well, is that investing in astronomy develops skills that are applicable way beyond astronomy. So in this case, I list a few data science skills that astronomy teaches. And of course, the maths, the statistics, the programming, analytics, and so on, but also the big picture thinking and the ability to learn make our graduates very adaptable. And so to stimulate that, we've embarked with a number of partners on a skills development program on using big data, research schools, and hackathons. So these are our partners in this program. And so for research schools, they're usually held over a week, or usually more, 10 days, sometimes 2 weeks, where we have students from a number of fields. It can be, it can be engineering, it can be mathematics, it can be astronomy, it can be physics, it can be, we bring them together for this period. They form groups, and they're each given a research project that they work on during that week. And we have a number of diverse topics. I'm going to show you that in a second. And we accompany this with industry skills development that I'm also going to detail in a minute. And this program is open to the AVN countries. So that's the 8 partner countries with South Africa in the SKA bit that I mentioned earlier. But that's the sort of focus area, but it's also open to other countries. So we've had events in Madagascar, twice in South Africa, and coming up in Kenya. in terms of the topics that we have, this gives you an idea of the sort of research projects that the students are working on. Anything from, you know, medical imaging to classifiers, recommendation engines, Internet of Things. So it's all very machine learning based to really develop those skills that come with astronomy, but are really in demand by industry. And when I talk about it in developing industry skills, we have a very cool sort of role modeling where these research groups suddenly have to think about their research as a product, and they have to think of their team as a startup. And we have this mock startup pitch competition with real industry players coming and giving them proper feedback, which is really a lot of fun. We also have mock industry interviews where, still playing the role of startups, they try to poach people from the other teams and hiring them. So they carry out industry interviews. So we have this sort of rotating role play that also is a lot of fun. And even though they themselves are not actually running companies, the fact that they play that role and interview people surfaces a lot of skills and experiences, and so they learn a lot from it. And then we also run a CV lab, because it often South African and African students, when they apply, say internationally, for example, their CVs are not very designy and they can be easily discarded. So we sort of teach them the latest trends in how to present themselves for, say, an academic, say a PhD position or a research post, or then how they present themselves to an industry job. For example, if they have a master's in astronomy, how do they apply for a data science job in an insurance financial services company, for example? So we try to help them, transition as well. And then we run hackathons. And so these are sort of shorter events where we have groups and they sort of delve into these projects very intensely over a couple of days. It's a classic hackathon format. At the end, they show presentations and the winning team gets a prize. And we've had these in person, also hybrid, and also fully virtually, because obviously the pandemic has redefined how we are able to do things. And so we've had events in Botswana, in Namibia, in South Africa, in Zambia, also a fully virtual Pan-African event that was really completely Pan-African. And we've also had Ghana, Mozambique, and Kenya. So this is really one of those, getting young people into the scientific fields. But as I said earlier, when I said that young people want to get rid of colonial heritage and that science wasn't spared, it's very true that science now is a sensitive topic, and the scientific community needs to engage in constructive efforts of transformation of the community. So transformation in South Africa means specifically getting a community to be representative of the population of the country. So if you look at the leadership in science in South Africa, it's very white dominated, whereas if you look at the population, 80% of the population is Black. So it's clearly not representative. So how can this be done? But attracting young people to science is not enough. And I just want to tell you a little bit of another story here, that the barrier of access to science for young South African Black children is much higher for anyone else, if anything, just because of language. And so this here is a map of the languages spoken in South Africa. So you see on the southwestern area, you'll see this turquoise color, which is Afrikaans. Afrikaans and English are the two languages of science tuition in the country. And if you look at the English-speaking areas, there's only two, these pale yellow things. One is along the East Coast, around the city of Durban, and one is sort of inland around the cities of Johannesburg and Pretoria. But the rest of the country speaks basically all African languages, first and second languages. And you can see this whole area as well to the north of Cape Town, where it's essentially white, and it says very sparsely populated. And that's obviously where the telescopes live. But if we look at the last census of the South African population, looking at English or Afrikaans being the language of tuition of science in South Africa, if we look at the ethnic group language distribution, we see that colored, white, and Indian people speak English or Afrikaans as first language over 90%, each of these. But the Black Africans, only 4.4% of them speak English or Afrikaans as a first language. But the Black Africans form up to 80% of the population. So that means that 80% of the population basically is very little English or Afrikaans first language. So this basically means that less than 5% of young Black children learn science in their first language. They learn science in the second or even third language, compared to over 90% of all the other ethnic groups in South Africa. And so this, you can imagine what a huge barrier to entry that is for young Black children in South Africa to join science and to study science. And this is really something that we need to work on. And so one of those things is that to create materials that are accessible. So this here is a copy of a very old career leaflet, trying to attract people to astronomy. And it predates the Meerkat, but you can see, for example, under characteristics of an astronomer, it says a serious interest in above average aptitude for physics and mathematics. So you can imagine how that will have put off a lot of young Black South Africans, regardless of talent, right? And so what we've done is we've developed a different set of resources and that we're trying to translate into African languages. But this is not trivial, we can't necessarily co-opt English terms directly. If we think of the scientific terms, a lot of scientific terms carry the history of how they came about in them, in their etymology. So for example, dinosaur means ancient lizard. We now know that they're not lizards, but that we just call them dinosaurs because that's the word for it. But when we try to create a scientific language, we have the opportunity to make this right and to correct scientific terms. And some scientific terms don't just have the scientific background, but they actually carry colonial connotations with them still. So what we do is we work with linguists, and here are a few of the things that we've come up with, is that when we try to create a truly indigenous scientific language to enable young Black children to learn maths and science with as much comfort and ease as other children in South Africa, we can use, for example, hooks from everyday life. So, for example, if we talk about radio astronomy, it gets confusing because the radio is something that people listen to. And it's very widespread in South Africa still to have a radio and to listen to the radio. And so we go from, instead of using the term radio, we use the term frequency because the radio DJs always talk about the frequency of their radio station. And so then people understand that this frequency is something that can change. So we talk about radio and we talk about frequency in astronomy. Other things that we can do is we can extend terms that exist already to give them a new meaning. So for example, if there's no word for astronomer in Zulu, for example, but there is a word for weather forecaster, because every day on TV you have a weather forecaster who comes and tells you the weather. And so by extending the word for weather forecaster into scientist of the sky, then we create a word for astronomer. Another thing is that we need to watch out for misleading terms. For example, if we say that astronomy is data intensive, the word data is not usually means the data credit that you purchase for your cell phone so that you can access WhatsApp and Facebook and so on. So using data, the word data has already been co-opted and has another meaning. So instead we use information. And so we say it's an information-rich science that then leads to knowledge, instead of just using the word data. And then we can elaborate on that. And another thing is that we need to seek in indigenous knowledge and indigenous languages words that already carry meaning, because a lot of indigenous knowledge, even though we think of them as being maybe sort of more like an ethnographic or traditional star lore, things like that, they actually incorporate knowledge that we consider modern science. So I'll give you an example of this. In isiXhosa, which is one of the South African languages, the word isilemela is the name given to the Pleiades. So why not take in that term and use the word isilemela to describe open clusters in isiXhosa? So those are a few of the ideas that we use to sort of try to develop an indigenous scientific language. So I've spoken to you about the Meerkat Telescope, about the incredible discoveries we made, and how we use the Meerkat as a way to bridge from these kids, looking at planet Earth, to developing skills, to being part of the incredible science that we are able to do here locally in South Africa with the Meerkat Telescope and also other facilities that we have. And I think this is a very cool adventure to be a part of, not just because of the science, but also because of the impact we're able to make the science have on our societies. And I would like to leave you with this invitation, because in 2024, the International Astronomical Union is having their General Assembly in Cape Town. In the over 100-year history of the International Astronomical Union, it is the first time ever that the General Assembly is held on the African continent. So we really, really want to make this General Assembly a different event. We don't want it to be just scientists sitting in closed rooms and talking about the latest discoveries. We want it to be an open event. We want it to be Pan-African. We want to bring Africa to the world. We want to open it to amateur astronomers, semi-professionals, astrophotographers as well. So we really want to organize this event completely differently from a purely scientific meeting. And as we say, this picture here is a picture of Cape Town. And we say, come for astronomy and stay for a holiday, or come for a holiday and stay for the astronomy. So I'll leave you with this invitation. And if you have any questions, I thank you very much for your attention.
That was a great talk. Thank you very much, Dr. Altman. I enjoyed every bit of it, all the information and all the stuff, the science aspect, the human aspect. That's just wonderful. Thank you very much. Oh, and I see we have already a lot of questions coming your way, but let me ask you first with the idea. I think you told us what it is and what an interesting infrastructure you have there, but you didn't tell us about how it was built. Did you actually have to lay down all those fiber optics between the cities? And what kind of workforce did you use to do that? How much indigenous South Africans were involved versus foreign investment? How was it built?
Thank you. Yeah, it's a really, really great question. So the fiber was laid down by SANRAN, that's the South African National Research Network. So joining the Square Kilometer Array was really a whole country effort. So when the SKA became a priority for South Africa, the agency in charge of the SANRAN said, okay, now we need to invest in infrastructure here. The agency in charge of for example, even South African tourism is promoting astrotourism in South Africa because this is now an opportunity. So every agency jumped on board with their area of expertise to make sure that everybody benefits from the investment in the Square Kilometer Array. And IDEA was set up thanks to a research chair, in fact, that was awarded. And the Meerkat is mostly South African built. It's been a great employment program. In fact, next to the Meerkat is another telescope, a radio telescope called the Hera, which looks at the epoch of reionization. And the Hera telescope is actually an American-led project, but the construction was fully South African. And in fact, they hired a team of unqualified. They had zero qualifications, so not even the end of mandatory school, after grade 12. But there's a lot of artisan skills, in South Africa, and in those rural areas where the telescopes are built, you don't really have access to a lot of schooling and not access to universities easily and so on. And so they were able to employ local people to build the Hera telescope. So yeah, there's very much a focus on empowering every layer of society when embarking on a project like this.
Wonderful, wonderful. And in terms of international collaborations, it's so important to keep the data there, and also, let others use that too. So do you also simultaneously send the data to some offshore countries, or is just there for you? And if anybody asks.
No, some of the data also goes offshore. The large survey projects, the 8 large survey projects, all of them have at least a South African co-PI, but they're all international teams. And in fact, the users of our cloud infrastructure are the whole research teams of those projects. So it's not just the South African researchers on those projects that are using the infrastructure, but also the researchers who are part of the collaboration but based elsewhere are logging into our facility to analyze the data. And I think the key here is that the cloud is proximal to the data, it's close to the data, and it's more important for the processing power to be close to the data than it is to be close to the user, because the visualization, the science results and so on, the outputs of all the processing are much lighter, obviously, than the raw data itself. And so we do have users from essentially the whole world, but it's most of it is PI'd or co-PI'd by South African researchers, which really places us on the map of radio astronomy globally. Well, it's had a fantastic effect, really.
And about that center you said about visualization, that it's also open to public. So you do accept people who come in and they request to see the visualized data. How does that work? Is that open? Like if you come there for the astronomy or for the holiday, where is it? Where can we visit that?
So the visualization lab itself is based at the University of Cape Town. And that's where the large screens are, and the immersive screen and the VR system obviously can be transported because it's based on laptops, but very powerful gaming laptops, of course, with GPUs, so that they're able to render the data using the VR software. But the digital planetarium is in the town of Cape Town, and it's part of Iziko Museums. So it's part of a museum. The planetarium is attached to the Natural History Museum in Cape Town, actually. And if you want to see some really cool dinosaur and whale skeletons, I highly recommend it. It's one of our favorite spots with my kids, obviously. It's an amazing museum. And that planetarium, half the time is for the public. And they have a cluster of computers just to render public shows and visualizations. And then they have a second identical cluster just for research. And so some of it is for astronomy, but there's also other research groups, like I showed you the mouse brain. There's, in biology, there's quite a few users who come and visualize and project the data on the dome to be able to look at it in an immersive way. And it's not just, it's not that they immerse and they go and measure with rulers and things on the dome. It's also about triggering the instinct of the researcher, because if you're immersed in your data, then you're triggered to look at this and look at that and what's there and what's that and so on. So it's really part of it sort of stimulates the human capacity for research that isn't equaled yet by any machine learning or AI algorithm at all, even though machine learning and AI are very much part of the research process nowadays.
And about the SKA observing, you mentioned that you have multiple modes of observing. And did I correctly understand that there's also a scanning part that you just survey the whole sky or part of it regularly?
Yes, so these large survey projects there's about half the time of the telescope is used for science, and the other half is, for calibration and things like that. So that's about normal. And in that 50% time, about 2/3 is for the large survey projects. And so some of them can happen, some of them use data of other projects. So for example, if one of the projects wants to survey a particular field of the sky, for example, then, and another project is also interested in that part of the sky, they can use the same data, right? But it does quite a lot of surveying indeed, yeah.
Okay, great. And switching to the science, we have some questions. So first of all, you showed that beautiful, beautiful picture of the galaxy with all those filaments and stuff. Can you translate some of the parts? Where are the visual things, located?
Right. Okay. So
we all used to the visual image of the Milky Way galaxy, but we have a hard time orienting ourselves in that radio image.
So I don't have it right here. I've done it, but I think it's on my other computer, which is this one. What you can do, so this is the center of the galaxy. It's not the entire Milky Way. So what you can do is you can take the optical image of the galaxy and you can overlay it with a sort of some transparency, and then you can see notably there's a few well-known bright objects. This is really Centaurus A, so you can see there's a few optical bright objects, and you can kind of align it yourself. So I've done it myself. So if you want to play around with that image and do that, you can do that, and then you can sort of see what scale compared to the usual image of the Milky Way that we know. So you can do that.
So it's just the almost just the center. Okay.
Yeah,
you said we're not sure about those like filaments that looks like scratches on old images.
That's a fun interpretation.
Yeah, sorry to put it that way, but
no, it's fine. So the filaments, look, it's unknown what they are. Some of it could be fronts, so shock fronts, say ejecta hitting a higher density area, and that causes like a front, for example. Some of it could be due to magnetic fields, with a lot of charged particles then, spinning around the magnetic field lines. We don't know yet. We just have to follow the papers that come out. There are so many structures, and some of these structures may look the same but have different causes. So it'll depend whether it's synchrotron or whether it's thermal or whether it's it's by looking at doing spectroscopic studies and optical counterpart, and also using other wave bands and multi-wavelength astronomy that will be able to do that. And that in itself is also not trivial, because some of those data sets, for example, if you put radio and optical together, optical will often be sort of more point source-like, and radio will be more diffuse. So, the ability to sort of position things accurately and center them and try to figure out, are they related or not, and things is also not a trivial process. So there's a lot of work that still needs to be done before we understand what we see.
Great, thank you. And in speaking of the history of some of these instruments, you mentioned that American built dish for communicating with satellites. That was the original purpose. So we have one question: can Meerkat and SKA be used to communicate with perhaps mission to planets in our solar system? Or
that's a great question. So what I can say, so we have a great PhD student, Brandon. His whole PhD is about satellite tracking. He takes all the signals from the satellites and tries to get them out of the signals so that we are sure that we actually get, data of cosmic origins as opposed to man-made signals. But it's a set of receivers and not emitters. So it wouldn't be used as communication dishes. It really just receives signals. So there's no emission capability in the telescope.
And the images you showed and the talks that you mentioned, they were all extragalactic or galactic images, can your facilities be used to observe the planets within the solar system, the gas giants specifically, in the radio spectrum? Or are they used?
Yes. Yeah, no, it can definitely be used for that. I think that all the science cases are a galactic or a lot of extragalactic, because the sensitivity of the instrument is such that it can go to, detect neutral hydrogen at very, very high redshift. So it really is designed for deep surveys. But there's no reason why it shouldn't be able to pick up the planets. I don't think it's in any of the projects. So it's not going currently as planned. I don't think that it's planned to point at any of the planets, but I'm sure planetary signals is also one of those radio frequency interferences that will be removed to gain access to more galactic and extragalactic signals.
Yeah, speaking about removing data, so one of the images you showed was all the radio galaxies in the field, and they were like a lot.
Yes.
And so the question is, so in that particular image, were all the other sources manually removed, or was it taken in a spectrum that other sources, including the stars in the Milky Way, were not emitting any emissions? So was it a cleaned image, in other words?
Let me go back to that image. Let me see again. I have a lot of slides. There we go. Okay. So no, I think they've all been any foreground objects have been removed. They can be removed automatically to a large extent, because we know their spectral properties, for example, and so they can be removed automatically. There's always a manual check, of course, as well. But it's not going to be, single object this, single object that. But there's so it can be removed, for example, knowing the map of stellar objects, that have been mapped in the distance between the telescope and those radio galaxies. But what's really cool here is that there is no there's an area around the center of the galaxy called the Zone of Avoidance. And it's when, we can't see through the center of the galaxy to see what's behind. And with the Meerkat, because it can see through molecular clouds and things, because it's radio, there's actually a giant cluster in Vela that's been discovered behind the center of the galaxy, a supercluster. So there's, the galactic stuff is indeed removed, and most of it will be automatic. But there were, we employ a lot of machine learning as well. So the machine learning algorithms have to be trained on manually flagged data, so that it can then recognize foreground objects and then remove them automatically. But we also face an interesting conundrum when it comes to using machine learning algorithms to clean the data, is that serendipity being one of the science cases, how do we make sure that we do not remove something that looks like noise, whereas it could be something that's never been seen before? And so we are very careful in terms of machine learning in what we throw away, because the data is just too large to keep. It gets reduced, and so it's kind of if you think of it as like a sampling frequency, you go from sampling every 2 seconds to every 8 seconds to every 30 seconds to every 60 seconds, to reduce the data. And we just try not to throw anything away that would be of any value.
Okay, great, thank you. And you talked about SKA. When is it expected to be completed?
A good question. So it's being built currently. So there's a prototype dish that's up already. I think there's a few SKA dishes that are up. So the Meerkat is 64 dishes. Now there's going to be an extended Meerkat with another 20 or so dishes, so it's going to be 80 something. And then SK phase 1 is going to be, I think, 700 dishes, so that's going to extend much larger. And the SK phase 2 is going to be the whole 3,000 dishes. The SK phase 1 is now under construction, and I think, let me see, I think they might start science operations in 2024, if I'm not mistaken. I stand to be corrected, though, that the exact timeline sort of, it changes. Except Meerkat was actually on time, on budget, and beyond specs, which is something that we're very proud of. Yeah. So, but it's the timeline. The exact timeline is regularly updated on the SK Observatory website. So that's where I would look to give you the latest information.
Okay, great. And nowadays, another topic which is quite hot are the gravitational waves. Somebody's asking about CARTA. Can it be used to get gravitational wave data?
That's a really interesting one. Let me think a second here. So gravitational wave data, I think, is quite different from any other format data that we use. So, optical data, we use the FITS format, it's straight imaging. Radio, it's calibrated luminosities in Fourier space that you then have to invert and convolve to get the images. Gravitational wave data, I think, is in a very different format. So I'm not sure if CARTA can be used for that. I think they have their own software tools. We have a conference soon. It's an annual conference. It's been going for 30 plus years now, called ADAS, which is Astronomical Data Systems and Software, or something like that. And it's actually in Cape Town in October, and there will be one gravitational wave data tutorial that I really look forward to attending to see how gravitational data is being used. But most of it uses the tools that astronomers use nowadays are the same as in data science. It's Python, it's Python libraries, and a lot of the software that we write are also in the form of Python libraries.
And speaking of CARTA, is it a software that can normal users install on their Windows machines, or do we need special machines to run that?
No, you can use the client and you can download it. Yeah, it's I think the URL is cartaviz.org.
Cartaviz.
VIS, yeah, cartaviz.org.
VIS.org. Okay, yeah. Excellent. And speaking of the capabilities of Meerkat telescopes, can they be used for the Doppler method of finding exoplanets by looking in the wobble of the stars?
The Meerkat, I think, is not really great at that, particularly. We have other telescopes in Sutherland where the optical and infrared telescopes are that survey the sky. We have one telescope that sort of takes wide field images all the time and is constantly looking for say variability, variable stars, and eclipsing binaries and exoplanets. So there's a lot of that done in the optical, but in radio, not so much.
Okay, and speaking of astrotourism, are any of these facilities open to public? Do they have open houses, or do they run visitor centers? Or if we come there, can we visit them?
Okay, so if you come to Cape Town, you can visit the observatory. There's open nights twice a month, and you can see the old historic telescopes from the 1820s, 1850s. And it's absolutely amazing. We have this old optical telescope with a moving floor, because the telescope is so big that the floor is on hydraulics to be able to actually see it. It's just wonderful. And there's the site in Sutherland where the optical telescopes are. So we have SALT, the Southern African Large Telescope, which is a 10-meter class optical telescope, which is like more or less like the Hobby Eberly telescope in the US. And it's an amazing instrument to go and see, because And so that site is open. So there's a visitor center. You can go there. You can plan. There's stargazing sessions, and there's, you know, the whole town is astronomy themed. You know, there's all the guest houses are named after Jupiter and Pleiades and, and Milky Way and so on. But the radio site is way too sensitive, in fact, to be open to the public. If you think about it, at the site itself, being, you know, the site is very extended. And so there's, you know, gravel roads going back and forth for technicians to access the dishes and things. But there's not a single petrol vehicle. It's all diesel, because petrol vehicles, as they fire, create a bzzzt of radio noise that would blind the receivers of the radio telescope. So that's how sensitive it is. There's absolutely no cell phone signal. It's an incredibly radio quiet area. It's surrounded by hills also to protect from man-made signals. And so there are sort of open days twice a year where they take a group of, say, I don't know, 40 people. They sort of cover all the receivers, and then people are allowed to go to site. But it's, I mean, the nearest town, and it's not a very big town, is about 80 kilometers away from the site itself. So that's, I don't know, maybe like 50 miles or so away. So it's gravel roads, you know, it's not, in fact, one of the first things, joke is that one of the first things that was built on site was an airstrip so that planes could land because it's so far from everything else. So yeah, if you keep an eye on the SARAO website and you time a trip to South Africa, well, you may be able to go to the Meerkat site. But I've only been I've been 3 times, I think, but only once since the Meerkat existed. I was there before when there was the precursor to the precursor, which was incredible. But yeah, it's a very, very special place. So if you get to visit it, it'll be amazing.
And you have a very impressive number of world-class astronomy facilities, and most of which have been developed in the recent past and ongoing. This implies a very large financial commitment for development operation. Can you comment on the financial flow and maybe foreign investment, or how much of it is funded by the government? How's that funded? And how's that working for South Africa?
So most of it is funded by the South African government, actually. There's a lot of engineering, for example, goes to tender, and South African engineering firms come on board and build things. And yes, it is a very big facility, and you know, we have a lot of astronomy, but that's because it started off just after the end of apartheid. In 1996, there was the department. So currently we have a Department of Science and Innovation. Back in 1996, it was called Department of Science and Technology and Culture, I think it was. And they published a white paper back then where they said it is important for South Africa to invest in flagship sciences where we have an advantage, such as astronomy, because of the quality of the sky that we have. And just for the sake of not taking a view of our nation as being forever tied to the treadmill of feeding and clothing ourselves, basically. So that's what it says. So it really says that, you know, if we see ourselves as a poor country that can't dream big, we'll never develop big either. And it's taken that view right from the beginning. It started with building SALT, and then it went on to the SKA and things. And it's always been with these programs to, you know, to uplift the society that go with it. And one of the things is that if you compare the fraction of the budget of the country that goes to science and to those scientific facilities compared to what goes to social welfare and, you know, social grants and things like that, it's actually very little. the cost of the social grants is much, much greater than the cost of astronomy. But astronomy is also a special science in South Africa. I'm not going to tell you that we have the same facility in every field of science. You know, there's a few fields of science where we sort of punch above our weight, if you will, and that's astronomy, is probably genetics, and conservation and biology. Because we have a couple of biodiversity hotspots in the country, and possibly nuclear physics, and also epidemiology because of the HIV epidemic. That has obviously been very dominant in Southern Africa. But other than that, if you take other sciences, we're much more humble. So it's really a strategic investment in certain areas of science where we know we have an advantage. So for astronomy, it's the skies, to the point where there's an act of parliament, the Astronomy Advantage Area Act, that protects this massive area in the Northern Cape Province, where the telescopes, the optical and the radio telescopes are, that protects them from development of, say, cell phone towers or light pollution and things like that. And it's set in law that this area needs to remain pristine for astronomy. And in fact, instead of hindering development, it's triggered some domestic development. So for example, the local telecommunications companies have developed directional cell phone antennae so that they can provide cell phone signal right to the edge of the field, but not interfere with the radio telescope, for example, right? So, and that's a technological development that has emerged from this domestic technological development that has emerged from this investment. So, yeah, it's a pragmatic but also ambitious approach.
Coming originally being from a developing country myself, I very much agree with this idea that if you just focus on feeding yourself, you're not going to be able to feed yourself in the future. So very happy to hear that that's the idea of the government to invest in that. And somebody's very curious knowing, do you have any numbers on the cost of SKA?
Ooh. Actually, I don't, but I know they're publicly available, but I don't have any numbers, not from the top of my head, no.
Okay.
Sorry about that.
Since you mentioned that you are very much, astronomers in general nowadays are very much using the same tools that computer scientists are using. Have you looked in, somebody's asking, have you looked in Tesla's dojo for computer processing?
Oh no, we haven't actually. We use OpenStack. We use all open source tools. So we use OpenStack for the cluster. We use a Slurm job scheduler for load balancing of jobs. We use just SSH. We use Globus, which is for data transport, which is a API and a data transport framework, but all of it is open source. We've built our own metal, basically. So we purchase our servers and we put them in our racks and we put them in the cupboards, and we have, we put in the air conditioning, we put in the power, the lighting. So everything from scratch. So we don't source cloud computing from any providers at all. And in fact, so we don't have this elastic capability. We have our resources, and we have to manage the load. So I don't know if I don't think it's cost effective for us to go to commercial providers, even though, interestingly, between the South African Astronomical Observatory and where the South African Radio Astronomy Observatory are based in Cape Town, there's a zone here with a massive development where Amazon is building a sort of a headquarters. So I don't know, maybe we should consider it at some point. But what's for sure is that this, we have this really good link to where the data comes at the Center for High Performance Computing. And I think this is a very important, it's very important for the processing facility to be close to the data.
And speaking of having your own processors, so nowadays a lot of AI is being done on GPUs rather than CPUs. So are you using GPUs too?
Yes. Yeah. We have some Tesla. Actually, it's Tesla 1000 something. So maybe we are using that. So we are using GPUs. Let me get back to the specs because I know.
Yeah,
I
sure.
have
While you're doing that, actually, someone commented that if people are interested in having a virtual tour of Meerkat, apparently the sites are visible from Google Maps. So
yes, that's right.
Yeah, that's actually true for most like large things. Yeah.
So in terms of compute nodes, we have 126 compute nodes. I think we have 6 GPU nodes that each have 32 CPUs and 2 GPUs on them, and they're Tesla 1000 GPUs. That's, I think, yeah, that's.
Thank you. And somebody asks about the frequency bands that are currently, Meerkat is currently using, and what are the frequency bands scheduled to be used by SKA?
So currently we have what we call the L band. I should really put up the website to give you the exact frequencies, because I'm not using them directly, but 1.4, 1.8 gigahertz L-band frequency is going full on. We're also currently setting up UHF and S-band receivers. So that's those are the 3 bands. But if you want the exact numbers of what those bands correspond to, I have to look them up. I don't have them. We're so used to just saying L-band, S-bands that we don't even think about numbers anymore.
well, we have a lot of ham radio operators, so I think they understand when you say that. And
okay, fantastic.
And let's switch a little bit about the people there. And first of all, let's ask about the access. So can you give us a little bit idea of the internet access in South Africa? Do normal people have easy access to internet, or the only way to get internet is expensive, as you mentioned, data packages provided by the cell phone providers? Can you give us an image of that?
Yeah, sure. So South Africa is very, is a country of extremes, right? So you can have the best quality and you can have no internet at all. We have a lot of rural areas. We have a lot of zones of no cell phone signal at all in the country. And in the rural areas where there is cell phone signal, it's usually edge or 3G. But then as soon as you get to urban centers, you can get 4G, and in some places 5G, like the bigger urban centers have 5G now. With the bigger urban centers also have, we also have fiber to the home in the bigger urban centers. So, the infrastructure is very well developed for the wealthy, and very much less so for the less wealthy and the rural areas that are isolated. But I guess it's a little bit similar in the US, right? You will have very sort of isolated rural areas that don't have that much infrastructure, and then you have your big urban centers that have the latest of the latest. So so I'm lucky enough to be talking to you over a fiber connection, which is, flows beautifully. In terms of undersea cables, we are not, we're not on the main backbone on the Northern Hemisphere, right? The London to New York and so on. But we have one backbone going from Cape Town to London. We have another one on the other side of the continent, along the East Coast, that goes via the Red Sea and via Cairo and across the Mediterranean. And sometimes that cable actually gets damaged. And then we're all like, oh, why don't these websites load? And it turns out that you can really tell the difference from where the places are hosted. And in terms of content delivery networks, there are not that many data centers on the African continent. They tend to be, in Europe and in the Middle East and North Africa, or even North America or South America. But if we're getting there, we're starting to get our own data centers, and obviously we have our own infrastructure. So Telkom, which is a South African phone service originally is now very much an internet provider, and they have data centers that they provide to businesses, and so on. So, we're getting there. Soon we won't feel so much when the cable is done, but it's usually like we have redundancy now, which we didn't have a few years ago in terms of international cables.
Okay, yeah, great. So speaking of areas without access, our very own observing site outside city, we had trouble for accessing internet for years, but now luckily we have fiber optics. So now you told us about all those fantastic programs you have in local languages. Can you tell us a little bit about the numbers? How many people have you reached? And how many people you have, or maybe it's too soon to tell, of how many people you've persuaded, how many people have actually chosen to go into university and follow an astronomy career?
Right. Okay. So I can tell you that, say, there's about 1,000 young people that have gone into science and technology, and mostly astronomy, thanks to this program. So this is really a massive change, considering that in 2003 there was about 2.5 radio astronomers in the country. So that's a massive growth. In terms of the language project, it is early days. So we've worked with linguists, but then the pandemic happened, and our plans to go testing it in schools and, testing the adoption and adapting it further. And I mean, we have 11 national languages. The testing was only planned in the Xhosa speaking part of South Africa, which is sort of the Western and Eastern Cape. But it's a similar group of languages to Zulu. It's a group of languages called the Nguni languages, but we also have languages in completely different groups, that like if you were to compare with European languages, you have the sort of the Latin and the Germanic group that are different. So similarly to that, you have different groups of languages in South Africa. So we haven't yet tested it a lot in schools. We're just waiting for this situation to calm down so that we can start doing it. But obviously the pandemic has also taken its toll quite a lot. And it's not just about waiting for the pandemic to sort of be over and some sense of normalcy to come back, but also a sense of prioritization. As soon as the situation calms down, it's about restoring the society. There's a lot of damage that's been done. A lot of kids have been orphaned. A lot of people have died. It's just, it's been, I think, traumatic all around the world, and it's really been quite terrifying. But yeah, so as soon as we get the chance, we'll pick that up again. And there's other people also who work in this area who try to do paleontology vocabulary, for example. And so I think this is really the beginning of a movement, if anything, to make science and mathematics and technology languages more inclusive in South Africa and across Africa as well, actually.
Okay, yeah, sure. Thank you. Looking forward to hear more about the program once the pandemic was over, and that was a fantastic program that you were saying. And speaking about development, we were talking before when we had the pre-meeting with you. You mentioned that some people, well, including me, were confusing the headquarters of International Astronomical Union being in South Africa versus the Office for Development is there. You mentioned a lot of programs that you were doing. You also mentioned that you have a personal connection. Can you tell us more about the role that International Astronomical Union is playing there, and all the other programs that are there? Is that?
Of course, yeah, of course, with pleasure. Yeah, I told you I was going to include some of it, but I think the content got so big in the end that I didn't want to add too many slides. I think it was long enough already. So the IU, about 10 years ago, just over 10 years ago, adopted a decadal plan where one of the efforts that they were going to focus on was the development of astronomy for development. How can astronomy contribute to development? And South Africa, with its approach, was a sort of a poster child for that. So it ended up that the IU set up an office for astronomy for development that is based in Cape Town, and that has been running for 10 years now, and it's run by my husband. So that's the personal connection. And this is an office that really looks at how can the fact that astronomy is being practiced contribute directly to socioeconomic development and to the sustainable development goals. And so this is beyond, the sort of long waiting time of technology spin-offs becoming mainstream, which can take, decades. This is more, how can we make sure that the community in a town where you have telescopes and therefore the town is not really allowed to develop because you don't want light pollution or anything like that, how can you make sure that the people in that town get opportunities similar to where you would have infrastructure that would interfere with the operation of a telescope, for example? And so those questions are all open. And it started off with projects like, building a community center in the township part of the town, where putting computers for the youth connected to the internet connection of the observatory, whereas there's basically no private internet, so that the youth at the end of school can go and hang out and discover the world through the internet, browse and everything, instead of having nothing to do and then ending up, carrying out mischief and things like that. And that has had a really good impact with, a corner for younger kids with books and, sort of supporting the education system. So that's one, all the way to having conversations about, developing eco astrotourism models with this project in Ladakh in North India, the Global Himalayan Expedition. So this is called the AstroStays project, to developing resources for blind people, for example, astronomy resources for blind people. And not just 3D printing surfaces so that they can feel, but also creating data sonification and using it for science, because the ear perceives things differently from the eye, in fact, in log scale, in fact. So that gives another way of exploring scientific data to, there's a lot of different projects that this office has explored. And since it's been established, it has established satellite offices, regional offices in different parts of the world. There are currently 11 offices. There's, I think, a couple that have to do with translation of projects and resources. There's a Portuguese one, and I think possibly another language one. Portuguese, obviously, because Brazil, Portugal, but even Timor-Leste in Asia and so on. Then there are these regional offices. The most recent one is a North American one, actually, that then try to replicate this model of having astronomy contribute to development locally. So it goes from, so in places where, in developed countries, it's more about inclusion and, you can have, astronomy, like stargazing and star parties in prisons, for example, and you can have things like that. And then you have things that are, for example, in Nigeria, you have a kit to equip a shipping container to become a sort of a mini science center that is pushed in a refugee camp for internally displaced people. And this sort of mini science center is accompanied by social workers and psychologists, so that young children and internally displaced people, refugees, are able to get mental health support while getting taught about astronomy and things like that. So there's the diversity of projects that have been funded in the last 10 years. So it's there's an annual call for proposals to fund projects, with the idea of these projects being upscalable, if you will. And so there's, you can look at it, the website astro4dev.org with the number 4, astro4dev.org, and you can see there's an incredible number of great projects. And in fact, so the annual call for proposals for this year is closed. It'll open again next year, I think around it could be as early as April, actually. But you can see also, you can look at the regional nodes and look at the North American one, because they're doing some really excellent work as well. And so maybe there's a possibility to participate.
Great, thank you very much. And as the last note, since you mentioned Las Cumbres Observatory, I can't not mention that OCA has actually a partnership with Las Cumbres Observatory's outreach program. We have a program called Cosmic Adventures, where we allow our members access to their 0.4 meter telescopes, and they could order images. So if anybody is interested, they could visit our website at ocastronomers.org and be part of that. Now, the question is, I know you do mostly radio astronomy. Are you in any case involved with Las Cumbres? And can you tell us a little bit about Las Cumbres in South Africa?
Sure. I don't know that much about Las Cumbres in South Africa specifically, but I know that there are a lot of people doing astronomy outreach in South Africa. And the Las Cumbres telescopes are based at the South African Astronomical Observatory, and they are fully robotic. So I think there are 4 telescopes, and they're fully robotic. So they're part of the global network of Las Cumbres telescopes. They are controlled from Cape Town, and then from abroad. But I know that with this investment, there's been quite a lot of outreach done by the South African Astronomical Observatory locally, but I can't tell you what exactly, because I know that they do a lot.
Okay, great. Again, thank you very much for a fascinating, great talk. And very much looking forward to hearing about SKA when it's fully operational. And I already know that Meerkat is doing wonders. Thank you very much again. And we still have questions. I apologize. We don't have much more time to cover all of them. And,
no, that's fine. Let me just show you something before we go. I just wanted to show you that the sun is rising here. So I'm going to just step outside quickly. And I'm going to show you the sunrise.
Oh, lovely.
Here you go. You see it?
Almost. Looks like your Wi-Fi is not very strong outside. Okay, yeah, we got the pic. Okay, thank you very much. That
okay, but you saw the pink, right?
Yes. So it's lovely to have this connection as sun has set already here, and then we have it rising there.
Yeah, so as you are about to go out stargazing, the sun has risen in this part of the world already.
Okay, lovely, great. Thank you very much. And let me thank our audience for staying with us this long. Please check the calendar on our website for all the upcoming events at ocastronomers.org. Thank you for joining us, and wish you all great times ahead. Thank you. Bye-bye.
Thank you so much. Thank you. Bye-bye.